Physics Part 240. Now it's your turn. A capacitor consists of two metal discs of a diameter of 15 centimeters separated by a sheet of polythene 0.25 millimeter thick. The relative permittivity of polythene is 2.3. Calculate the capacitance of the capacitor. Capacitors in series and parallel. Well, the figure shows that the two capacitors of the capacities C1 and C2 are connected in series. We shall show that the combined capacitance C is given by 1 over C is equal to 1 over C1 plus 1 over C2. If the voltage across the equivalent capacitor is V and the charge stored on each plate is Q, then V is equal to Q over C. The potential difference across the combination is the sum of the potential difference across the individual capacitors. V is equal to V1 plus V2, and each capacitor has the charge of Q on each plate. A charge of plus Q induced on one plate of one capacitor will induce a charge of Q on the plate of the second capacitor. Since V1 is equal to Q over C1 and V2 is equal to Q over C2, then Q is Q over C minus Q over C1 plus Q over C2. Q over C is equal to Q over C1 plus Q over C2. Dividing each side of the equation by Q, we have 1 over C is equal to 1 over C1 plus 1 over C2. A similar result applies for any number of capacitors connected in series. The reciprocal combined capacitance equals the sum of the reciprocals of the individual capacitance in series. Note that for two identical capacitors in series, the combined capacitance is equal to half of the value of each one. For a capacitor in series, the combined capacitance is always less than the value of the smallest individual capacitance. In figure, the two capacitors of capacitance C1 and C2 are connected in parallel. We shall show that the combined capacitance C is given by C is equal to C1 plus C2. If the voltage across the equivalent capacitor is V and the charge stored on each plate is Q, then Q is equal to CV. The total charge stored in the sum of the charges on the individual capacitor is Q is equal to Q1 plus Q2. Q is equal to Q1 plus Q2, and there is same potential difference of V across each capacitor since they are connected in parallel. Since Q1 is C1 into V and Q2 is equal to C2V, and then CV is equal to C1V plus C2V. Dividing each side of the equation by V, we have C is equal to C1 plus C2. The same result applies for any number of capacitors connected in parallel. The combined capacitance equals the sum of all the individuals' capacitance in parallel. Note that the equation for the capacitors in series is similar to the equation for the resistance in parallel, and the equation for the capacitor in parallel is similar to the equation for the resistors in series. Examples. Number 1. A 100 U farad capacitor is parallel with 50 U farad capacitor is connected to a 12 voltage supply. Calculate the total capacitance. Calculate the potential difference across each capacitor. Calculate the charge stored on each capacitor. Number 2. A 100 U farad capacitor in series with a 50 U farad capacitor is connected to a 12 voltage supply. Calculate the combined capacitance. Calculate the charge stored by each capacitor. Calculate the potential difference across each capacitor. Now it's your turn A 470 U farad capacitor is connected with the supply. Calculate the charge stored on the capacitor. The capacitor is A in the disconnected form, and the supply connected to an uncharged 470 U farad capacitor. Explain why the capacitors are in parallel rather than series, and why the total charge stored by the combination must be the same as the answer to A. Calculate the capacitance of the combination. Calculate the potential difference across each capacitor. Calculate the charge stored on each capacitor. We'll discuss further charging and discharging capacitors, and we'll have more on it, but right now we're going to have a pause to it. That's all for the day, and I'll come along with more videos of the next day.